Okay, so this is the fourth lecture of MAT 212. Today we'll be looking at elementary matrices. The first thing we do is we review elementary row operations, as in the ones listed here. So what are elementary row operations? The elementary row operations that we are allowed are: 1, we multiply the ith row by a non-zero constant c, which is not equal to 0, so which turns the ith row into a multiple of the ith row. So if you have this matrix, you multiply the second row by some constant c. For example, if you multiply the second row by 2 times r2, that gives you 1, 2, 6, and 8. The inverse is, of course, multiplying the ith row by 1 over c times ri. So that brings you back to the original matrix. So if you do half r2, you end up with 1, 2, 3, 4, which is the original matrix that we started with. So the inverse row operation reverses the effect of the elementary row operation. Now the second row operation is interchanging two rows, meaning if you start with this matrix 1, 2, 3, 4. So if you do r1, r2, then you get 3, 4, 1, 2. You interchange the first and second rows. Now, doing the same operation again is going to give you back the original matrix. So it's going to put 1, 2. Is going to put 1, 2 on top and 3, 4 below. And the third elementary row operation is adding a multiple of another row to a particular row. So for example, you start off with this guy, 1, 2, 3, 4. Then you add 1/3 of r2 times r1. So r1 becomes 0, and of course 2 plus 4 over 3 is 10 over 3. 3 and 4. So the inverse operation would be subtracting 1 over 3 r2 from r1, which would give back the original matrix. Okay, so let's get rid of everything now. Okay, so let's erase this. It's not working out. All right, so if you okay, so now that we've looked at the row operations, let's define what an elementary matrix is, right? Now, if you can get okay, so if you start off with the identity matrix in any number of dimensions, let's start off with the identity matrix in 2 dimensions. 0, 1. You perform an elementary row operation. Let's say you do 2R1, right, and you end up with 2 0 0 1. Well, since you got from the identity matrix to this matrix using a single elementary row operation, you could call this we call this an elementary matrix. So an elementary matrix is simply one that can be obtained from the identity matrix using the keyword being here, single elementary row operation. Okay, now we define another term, row equivalence, which is if you have two matrices which can be obtained from each other by a sequence of elementary row operations. Now they may be by one or more elementary row operations. You call them row equivalent. Okay, so let's state a theorem about elementary row operations. The theorem is simply this. It's that if you have an elementary matrix E, right, that corresponds to a particular elementary row operation, right? So for example, so we look at the elementary matrices here. So if you have that and you left multiply any matrix, of course, as long as if you're allowed to left multiply any matrix that you're allowed to left multiply by that elementary row operation, then the result will give you the result is the same as if you would have would have performed an elementary row operation on that matrix. So for example, if you have an elementary matrix if you have an elementary matrix E, right, so which is, let's say, M by M, because elementary matrix is always square, and you have a matrix A which is M by N. Of course it has to have M rows. Now EA, this product is the same as A with an elementary row operation, right? What elementary row operation is that? That elementary row operation, the one that corresponds to E, right? So this product, so the theorem basically says that if the elementary matrix E results from performing a certain row operation on IM, and A is an M by N matrix, then the product EA is a matrix that results when the same row operation is performed on A. Okay, so let's illustrate before we try to prove the theorem, right? Let's illustrate this as an example. See if we understand the theorem. So remember, we have the from the previous lecture, we have a 3x4 augmented matrix A. All right. Now, in the previous lecture, what we did was we tried to bring this matrix into row echelon form using Gauss-Jordan elimination, right? So remember, if it's we tried to bring this into reduced row echelon form. So if it's reduced row echelon form, we call it Gauss-Jordan elimination. Alright, and if it's a row echelon form, we just call it Gaussian elimination. Okay, so we started with A. So the first thing we did was we subtracted twice R1 from R2. Now, what is the elementary matrix corresponding to the subtraction? Well, let's call it E1, right? So this is minus 2 because this was originally 0. So 0 minus 2 times 1 is minus 2. 1 minus 2 times 0 is 1. 0 minus 2 times 0 is 0. So this is the elementary matrix corresponding to this reduced row, corresponding to this elementary row operation. Now if I multiply E1, if I right multiply E1 by A, right, so this is my A, and this is my E1, I get A1, right, which is, notice that A1 is exactly what you would have gotten if you had just performed this elementary row operation on A, right? Now, similarly, the next elementary row operation is R3 goes through R3 plus R1. Now, what is the matrix, the elementary matrix for this elementary row operation? So, this is the elementary matrix for R3 goes to R3 plus R1, this guy over here. Now, notice that the first and second rows are unchanged, of course, and the third row is 1, 0, 1 because you just added it to the first row. So you multiply this to the to A1, and you get A2. Now A2 is basically what you get if you do. A2 is exactly what you get if you perform this elementary row operation on A1. Right, R3 goes to R3 plus R1 on A1. Now, of course, similarly, you have the next elementary row operation we do is R1 goes to R1 over 2. So the corresponding elementary matrix is this. Notice that only the first row of the matrix is divided by 2 because it's R1 over 2. Now, you multiply A2 by this elementary matrix and you get what you would have gotten by just performing the elementary row operation on A1. On A2. So, and you end up with A3. So now, your exercise is to write down the elementary row operations, the elementary matrices for the rest of the elementary row operations until we get to the reduced row echelon form, and to of course show that left multiplying by those elementary matrices has the same effect as performing the elementary row operations. Okay, so now that you've understood what this theorem is, let's prove it. Okay, so let's so of course you let IM be the M by M identity matrix and A be the M by N matrix, right? So let's prove this theorem, right, for each of the row operations that we see in part 1. Okay, so let's start with multiplying a row by a constant, right? Okay, so let's see what happens when you multiply a row by a constant. So the corresponding elementary matrix E is the same as IM, except that the entry in the jth row and the ith row in the ith row and ith column equals C, meaning E I equals C, right? And all the other diagonal elements are so E K equals 1, when k is not equal to I. So all the diagonal elements are 1, except for EII, which is equal to C. And the rest of the elements in the matrix are 0. Okay, so you use the rules of matrix multiplication to add them up, or to multiply them, and you end up with, okay, so and of course you end up with so EII and times AIK. Now, since this is the identity matrix, right? Except that the now what we're doing is we want the ith row and the kth column, right, in EA, right? So we want the element in the ith row and the kth column in EA. So with this stipulation, right? Now, of course, this is given by the summation over L of EIL times ALK. Now, EI, the only time EIL is non-zero is when L equals I, right? When EII equals C. And so this is C times AIK, right? So L equals I, and we end up with CAIK. So notice that the element in the ith row and kth column of A is multiplied by C. So this is basically the effect of performing the elementary row operation on A. Okay, so similarly, we prove the other two. We prove the theorem for the other two elementary row operations. If you switch the ith row and the jth row, for example, we know what the elementary matrix is going to look like, and we've used the rules of matrix multiplication to show that left multiplying by that elementary matrix is the same as switching the two rows. And we also do it for the other case, when we adding a multiple of one row to another row, right? When we do that, you know what the elementary matrix is going to look like, and you use the rules of matrix multiplication to show that left multiplying with the elementary matrix has the same effect as performing the elementary row operation. Okay, so that's that, and of course you know what the inverse. You know that there are, for each elementary row operation there is an inverse, right? And the inverse of the elementary matrix is the elementary matrix that corresponds to the inverse row operation. So the easy way to prove this is to see that if is this, right? If you notice that if E is an elementary matrix, right, and E prime is a elementary matrix corresponding to the inverse row operation, right, that E corresponds to, then the effect of E and E prime, they cancel out to give you I. So E prime brings E back to I. So therefore E inverse equals E prime. So that's how you invert an elementary matrix. Okay, so now what we're going to do is we're going to look at a bunch of equivalent systems about square matrices, right? So when I say that these are equivalent statements, right, what I mean to say is that either all of these statements are true or all of them are false at the same time. You're never going to have one of them being true, another of them being false, and so on and so forth. Right, so in this course, in total, we will have 21 equivalent statements. Now, as we go along, we'll learn more and more about, as we go along the course, we'll learn more and more about these statements. However, for the first chapter, we'll for this lecture, we'll look at 6, right? So first we'll prove 4, then we'll prove 2. So let's see what these equivalent statements are. So you start with a square matrix A, right? That is, I think, which is n square matrix A. So you look at the theorem in the red box, right? So you start with an n square matrix A and an n-dimensional vector x boldface, right? So we have a bunch of statements about them, right? So A is invertible, meaning A is non-singular. The system of equations Ax equals 0 has the trivial solution. So if you remember, Ax equals 0 is the system of equations that is given by A11 x1 plus A12 x2 plus ... plus an xn equals 0, and then all the way to a n1 x1 a n xn equals 0, right? So this set of equations has only the trivial solution. Trivial solution. Meaning the only solution to these equations is x1 equals 0, x2 equals 0, all the way to xn equals 0. Now, that's the second statement. The third statement is that the reduced row echelon form of A is in. Okay, so if you perform Gauss-Jordan elimination on A, you will end up with in, the n by n identity matrix. And the fourth statement is that A can be expressed as a product of elementary matrices. Okay, so let's start proof. Now, how are we going to prove that they're equivalent? That these statements are equivalent? Now, of course, when two statements are equivalent, it means that either both are true or both are false. When forced, so any number of statements are. So we have to prove this is an if and only if proposition, meaning we have to prove the statements in both directions. So what we're going to do is we're going to prove. We're going to use 1 to prove 2. We're going to use that to prove 3. We're going to use that to prove 4. And we're going to show that 4 implies 1. See this blue diagram over here? This one? This is how we are going to prove it. So we're going to prove that 1 leads to 2, and 2 leads to 3, and 3 leads to 4, and that 4 leads to 1 again. So that tells us that the 4 statements are equivalent. This is an if and only if proposition. Okay, so let's take 1 to be true. A is invertible. Now, if A is invertible, and you have Ax equals 0, right? Then A inverse A times x equals 0, or x or Ix equals 0, or x equals 0, right? Now this means that x, so since x is a column vector, right? So this should be a vector. This is the 0 vector. since this is an n-dimensional column vector, right? So which means that all the components of x are equal to 0. All right, all the components of x are equal to 0. So this gives you the trivial solution. Now, what about the reduced row echelon form of A being equal to in? Now, notice that if I have ax equals 0, all right, so this is the expanded out form, right, of the system of equations. Expanded out, right? Now, of course, this now since this has since we have taken for granted that since we have hypothesized that this only has a trivial solution, the reduced row echelon form must be this guy, right? So this is not the reduced row echelon form. This is a row echelon form, actually. This is the reduced row echelon form. Sorry, this is a reduced row echelon form, but this is written out in a non-matrix form. This is an equation form, right? Now we can rewrite these two guys, this guy and this guy, in augmented matrix form. So this is the set of equations. This actually corresponds to this. This is a set of equations in augmented matrix form, right? So these guys, they're the same. And this is a reduced row echelon form in augmented matrix form, right? Now notice that the reduced row echelon form is the same as the okay, so notice that the matrix that is on the left of the barrier, imagine that the barrier is not there. Okay, so the identity matrix, the n by n identity matrix. So this proves our proposition that 2 implies 3. Now, how are we going to show that 3 implies 4? Now, remember, we have to show that using the fact that the reduced row echelon form of A is I, right? We have to show that that A is a product of elementary matrices. Well, the way to do this is to first note that multiplying by a set of elementary matrices is going to bring you into reduced row echelon form, because how do you get to the reduced row echelon form? You get to the reduced row echelon form by doing elementary row operations. One way of doing elementary row operations is by multiplying by the elementary matrix, by left multiplying by the elementary matrices that correspond to those row operations, right? So let's say you need k row operations, right? So for each of those row operations you need an elementary matrix, all right? So each of these row operations you need an elementary matrix. So you multiply that by A, you get I, right? So this tells me that A is going to be equal to the inverse of the product of these guys. This is equal to A. And of course, this inverse is E1 inverse times E2 inverse all the way to EK inverse. Now, remember, what do E1 inverse, E2 inverse all the way to EK inverse, what do they give you? Well, what are they? Well, they are the elementary matrices that represent the inverse transformations of E1, E2 all the way to EK. So we have proven this. So the inverses of these elementary matrices are also elementary matrices, and we've proven that A is expressible as a product of elementary matrices. Now that we've proven that A is expressible as a product of elementary matrices, we need to prove that A is invertible? Well, meaning our last statement that 4 leads to 1, right? This statement here, that 4 leads to 1. Now, since A is a product of invertible matrices, right? So any product of arbitrary product of elementary matrices should any product of invertible matrices is invertible, right? This actually follows from something you've shown in your lectures, in your assignments, sorry. And of course, we're going to go over this same problem again. However, now you've proven this for two matrices, for 3 matrices. We're going to have to prove this for an arbitrary number of matrices, for n matrices, that any product of invertible matrices is invertible, right? Now, but you don't really need to prove it. You can actually, okay, so we can, but it's pretty easy to prove this, right? Just say that. Okay, so we use a constructive proof. Well, what it means is we propose that the inverse of A is EK times EK minus 1. We propose that A inverse, right, equals EK, right, times EK minus 1, basically in the opposite direction, right? You're multiplying in the opposite direction. So and of course remember your A was what? A was E1 inverse, E2 inverse, all the way to EK inverse, right? So you multiply this by this and you get I, right? You should actually show this, right? So since we've managed to find an inverse for A, obviously A is invertible, right? And this actually completes our proof. So 4 implies 1, which implies 2, which implies 3, which implies 4, which implies 1, which implies... So what we've done, we've shown that the 4 statements are if and only if, right? Meaning they are equivalent, they're necessary and sufficient. I mean, you would use the words necessary and sufficient to describe the relationship between them. Okay, so we have the this set of equivalent statements, right? And from this set of equivalent statements, what we can do is we can form an algorithm to find A inverse, right? Notice that we've already found A inverse, right? So A inverse is the is basically the product of elementary matrices, right? The product of elementary matrices that you need to bring A into reduced row echelon form or the identity matrix, right? But in the opposite, in the reverse order, right? So this actually gives you an algorithm, right, or a series of steps to find A inverse, right? How so? Well, if you perform the if you perform, right, the elementary row operations, right, that bring A into the identity, that transform A into an identity matrix, right? So if you perform those operations on the identity matrix itself, right, you will get A inverse, right? Isn't that what this equation says? That A inverse is the product of these guys. So you perform E1 first, and E2, and then E3, and all the way to EK. So let's say I give you this matrix, right? A. Okay, so this is matrix. This is the matrix 2, be inverted, right? So what we do is we make an augmented matrix, right, out of A and I, right? So this is A, so this is I. So we will perform, so the elementary row operations that bring A to I, the elementary row operations, EROs, that bring A to I are the same elementary row operations that bring I to A inverse. That's the basic idea, and that is what this equation tells you. That is what this equation basically tells you. All right. Now, I've given you an invertible matrix on purpose. If the matrix weren't invertible, then the reduced echelon form would not be I, of course. So you perform the same elementary row operations on A and on I, and of course you bring A to I, right? You transform A into I, right, using these operations, and whatever happens to I is what your A inverse is, right? So this is your A inverse. So then, so the exercise basically gives you the matrix, and it asks you to invert it using the given algorithm, right? So now we turn our attention to how many solutions a given system of equations may have, right? So if you have a system of linear equations, right, any system of equations, right, you can have 0 solutions, you can have exactly 1 solution, or you can have 2 or more solutions, right? Now, with the system of linear equations, it's the same, right? You can have 0 solutions, you can have 1 solution, or you can have 2 or more solutions. But the only difference here is that if you have more than 1 solution or 2 or more solutions, you'll have to have infinite solutions, right? So what we end up with is that a system of linear equations, right, has either no solutions right, or exactly 1 solution, or infinitely many solutions, right? So these are the 3 options, right? No solutions, exactly 1 solution, or infinitely many solutions, right? Now we get when we can have no solutions. You've seen that in your assignments, right? We see when you have exactly 1 solution, right? In 2 dimensions, it's when 2 lines intersect, or in 3 dimensions, it's when 3 planes intersect. How about the infinitely many solutions part, right? If, for example, if 2 lines are 2 parallel lines, right? And if 2 lines are basically the same line, right? You expect them to intersect at every point. And that's how you get infinitely many solutions. But we're talking about the general case here. We're not talking about 2 dimensions or 3 dimensions. We're talking about n dimensions, right? So let's say you have 2 solutions, right? Let's say ax equals 0 has 2 solutions, right? So let's call those solutions x1 and x2, and let c1 and c2 be 2 real numbers that are not 0. So if those are solutions, if x1 and x2 are solutions, then ax1 must be 0 and ax2 must also be 0, right? Now, in that case, a times c1x1 plus c2x2, any linear combination of those 2 solutions, right, equals C1 times AX1 plus C2 times AX2, with AX1 and AX2 are both 0. So this is C1 times 0 plus C2 times 0, which is 0. Right? Which is 0 plus 0, which is 0. Now, so if you have two solutions, then any linear combination of those two solutions gives you another solution. Now, since there are infinitely many linear combinations of two solutions, you can choose any C1, you can choose any C2 you like. So the number of solutions goes all the way up to infinity. So this gives us a new theorem, which is that a system of linear equations can have 0, 1, or infinitely many solutions, right? It can have no solutions, it can have one solution, or it can have infinitely many solutions. Okay, so our next theorem, right, what we're going to do is we're going to show that if A is our next theorem basically says that if A is an invertible n by n matrix, right, this guy, this theorem, right, if A is an invertible n by n matrix, and if V is an n by 1 vector, right, then the system of equations Ax equals V has exactly one solution, namely x equals A inverse B. Okay, so there's exactly one solution. Now, why is that? Okay, so let's say you have one solution. So first of all, what we do is we're going to show that A inverse V is a solution. How do we show that? We plug it in the original equation. To show that something is a solution, we plug it into the original equation. So A inverse V hat equals A inverse, sorry, not V hat, V underline, right? Now, this is of course the n by n identity matrix times V, which is an n by 1 vector, so which gives you V. So I know that this is a solution. Now, if this is a solution, okay, so we've proved part of the theorem. We've shown that this is a solution. Now, if this is a solution, now let there be another solution. Call that other solution x naught, right? So if x naught is a solution, right, then it must be true that A times x naught equals V. I'm sorry, there's a typo here. This should be A times x naught equals V, right? Not A times x naught equals 0. So x naught equals A inverse V, right? So any other solution has to be equal to A inverse V, because if I multiply both sides by A inverse, so A inverse on this side and A inverse on that side, right? And you associate A inverse and A on this side, so you get an IN here. So IN times x naught equals A inverse V, or x naught equals A inverse V. So any other solution must also be equal to A inverse V. So therefore, the only unique solution you have is x naught equals x equals A inverse B. Now, please note the typo. This should be V. I'm going to fix this later on. Okay, so now we can add two extra statements to our set of equivalent statements. So we already had the first four statements, right? A is invert. We've already proven the equivalence of the first four statements, right? We've shown that this statement, the reduced row echelon from this statement, and A being expressed as a product of elementary matrices, this statement, we've shown that these are true. Now we're going to show that 6 okay, so we're going to show that 1 implies 6, and then 6 implies 5, right? And 5 implies 1. So we're actually, what we're doing is, so 1 implies 6, which implies 5, which implies 1. So this tells us that 5 and 6 are both equivalent to 1, right? Equivalent to 1, right? Now, if 5 and 6 are equivalent to 1, they're equivalent to 2, 3, and 4 as well. Because 1 is equivalent to 2, 3, and 4. So if 5 and 6 are equivalent to 1, then 5 and 6 are equivalent to 2, 3, and 4. Okay, so let's try proving 6 from 1. Now, 1 says that A is invertible, and 6 says that Ax equals V has exactly one solution for every n by 1 matrix V. But isn't that exactly what we've proved here? Right? This is exactly 1 going to 6, right? 1 implying 6. And 6 implies 5, right? Now, since what is 5? What does 6 tell you? This 6 tells you that Ax equals B has exactly one solution for every n by 1 matrix B. And statement 5 says that Ax equals V is consistent for every n by 1 matrix V. Now, of course, if a system of equations has no solutions, it's an inconsistent system. And if it has one solution, then it's called a consistent system. If it has one or more solutions, then it is called a consistent system. Now, if it has exactly one solution, of course it's consistent, right? So 6 implies 5. Now, what about 5 implying 1? So what does 5 tell you? That 5 tells you that Ax equals V is consistent for every n by 1 matrix V. All right. So if it's consistent for every n by 1 matrix V, then it is consistent for the matrices that are for the unit vectors V, right? In the n different directions, right? So take this to be your V equals E1, right? So this is E2 all the way to En, right? So E2 has 1 in the second position, E1 has 1 in the first position, and En has 1 in the nth position, right? So these are all consistent. These guys are all consistent. These are all consistent. So if these guys are all consistent, then what you do, you let the solutions to these equations, right, be x1, x2, all the way to xn, right? And you form a matrix C with these solutions, right? So the first column of the C is x1, second column of C is x2, and the n all the way to nth column is xn. Now, of course, in that case, AC, the matrix, would be ax1, ax2, all the way to axn. Now, but these guys, what is ax1? ax1, remember, is a solution to ax equals. What is ax1? ax1 is a solution to. Sorry, what is x1? x1 is a solution to this guy, right? To this guy, right? So ax1 must equal 1, 0. ax1 must be equal to this, right? And so on and so forth, right? So ax2 is, so this is 1, 0. So, and AX2 is 0, 1, right? And what is AXN? AXN is 0, 0, 0, all the way to 1. Now, these are the columns of the n by n identity matrix. So now what have we done? We have shown that AC equals I. So this tells me that C must be equal to A inverse, right? Now, if that is the case, then since we have already found an inverse for A, so we know, so it's pretty obvious that A is invertible. And of course, the last exercise tells you to look up examples 3 and 4 from pages 65 and 66 of Howard Anton's book. So this is important for your midterm exam and for your assignments. You'll have to look at you have to study these examples for your to understand when there are infinitely many solutions and when there are no solutions. All right, so that's the end of your 4th lecture. I understand this was very heavy on proofs. I hope to have a small live lecture with you on proofs. But this lecture, along with the 3rd lecture, they are sufficient for you to answer all the questions on assignment 2. All right, so that's the end of that. Thank you very much.